My name is Arvid, and I'm going to talk about Merkle sets today. And this is like an anecdote of something that happened at my work. And I'm not entirely sure yet what the moral of the story is yet, but maybe we'll come up with something at the end. I will cover 3 topics. First, introduce what the Merkle set is, and then introduce you to the textbook sort of standard solution that comes to mind, and then sort of the plot twist at the end with how you can think of this problem from a slightly different perspective and come up with a, I would say, simpler solution and better in many aspects, but we'll see. So let's start with the Merkle tree. So Merkle tree is where you have a tree with leaf nodes, and each internal node is the hash of its children. And then at the top, you have the root hash. So that root hash represents the whole tree. So there are 2 kinds of nodes, the internal ones and the terminal nodes. I'm going to call the leaf nodes terminal nodes. So these are the internal ones. These are the terminal ones. And that the root of the tree. So what's the point of having a root of a tree like this? Well, the main feature that I'm going to use as the use case here is you can present something that's called proof of inclusion. So if you have a tree, if you have a root, I only know the root. Someone else who knows the whole tree can prove to me that an item is included in the tree without sharing the entire data set with me. So, for instance, you can think of a database table. I don't know the database table, I just know the root of it. Someone that has the data can prove to me that this row in this data in this table is included in the table, and here's the proof, and it's going to be a short proof. Specifically, if you want to prove that D is part of this tree, all you need to include in the proof is D, the hash of C, and 5 and 2, and then I can reconstruct the root from those nodes as the recipient of the proof. I don't know, is that obvious how I would do that? Right, with the hash of C, I can compute 4, and I have 5, then I can compute 3, and with 2, I can compute 1. And if it matches my root, I know for sure that D is included. You can also do things like proof of exclusion. If you, for instance, have another constraint that the leaves must be sorted by a certain way, you can say that in this location where this item would have been, it's not there, basically. But let's skip that. So this is a tree. If we want it to be a set, then we want the same items to always yield the same root. So that means it's not just, you can't order it willy-nilly and make any kind of tree. It has to be deterministic. So for example, here are 2 examples of the same leaves, but they would give you different roots because the layout of the tree is different. So not only do you need to sort the elements, you also need a deterministic way of actually building the tree to have this feature. So one way you can do this is to just decide that you build the tree by looking at a bit, and you go either to the left or to the right. So if an item first bit is 1 or 0, you go to the left. If it's 1, you go to the right, and so on. So you get something like this. Let's say you have ABC. B and A start with 0, so they are on the left side of the tree. C starts with 1, so it's on the right side of the tree. And as long as you use a good hash function or a cryptographic hash function, your tree will be quite balanced. Right.
So was this on the hash or on the actual data? The bit from the hash from the data?
From the hash. Yeah, I'm going to mix the item itself and its hash. But right, you typically need to hash the data first.
But another question, if you have two identical leaf node values.
Aha, exactly. That's my next point here. If you have a deterministic layout like this, you will be able to find duplicates and deduplicate them just like you would want to in a set. Right? If you insert the same item twice, it only exists once in the set. So that's another important feature. However, this opens a new problem that we didn't have previously. You can have holes in the tree. You have places where there is no node. For example, if ABC would have had these values instead, like there is no item that starts with 3 zeros, and there's no item that starts with 0, 1, right? But the layout mandates them to be in this layout. So we need to add a third node called an empty node to just fill in the blanks where that happens. All right, that's a Merkle set. Easy. So the textbook version of this, as I will refer to it, or merkleset.py, we have a tree. We have 3 different kinds of nodes in the tree. It's like we have a base class, and we have 3 different classes that derive from it. So we have the node. What can you do with the node? You can compute its hash, and you can add another node that then sort of trickles down and is inserted in the right place. And then we have terminal nodes, middle nodes, and empty nodes. Easy. And so the way you would build a tree is you start with an empty node, you call add on it, it turns into a terminal node. You call add on that, then it needs to think a little bit. It needs to create a middle node, but it doesn't really know exactly what's going to happen. So it creates the middle node, looks at the 2 terminal nodes that it now has. They're like put on the side there and being inspected. And maybe it realizes that, well, it needs to create an empty node because both of them are on the right side. And so then it has to call make middle again to create another middle node, and maybe the tree ends up like this. So just to make it entirely obvious how this would work, if you add another node, you start calling add on middle, it trickles down, and then we're back to now we have to make another middle node, and we think about it, and then perhaps the tree will look like this. Make middle is a pretty simple Python function in this case. So the children, it's a tuple of 2 items. The depth, we have to know which depth we're at because that's determining which bit we're considering. At the beginning, we look at the first bit. At the next level, we look at the second bit, and so on. So there are 2 cases in this function. One is get bit, child hash. So we look at the bits for both child nodes. If they are different, then we're done. Then we just create a middle node, and those children are on each separate sides. However, if they're not, then we need to figure out which side the empty node goes on into, and then the other side where the empty node isn't, we create another middle node and recursively sort of trickle down. So one of the operations we want to do on this is to compute the root. And as you can imagine, when we have this tree structure, it's pretty straightforward. It's just a recursive function calling get hash on its leaves. So we call get hash, we get hash back. Call get hash, it has to recurse down. Call get hash, recurse down. Call get hash, and we build it up, and then finally we have the root hash. This is about 285 lines of Python code, and it's quite slow because it allocates objects when you add nodes to the tree, and they're all spread out on the heap. So now we get into the thinking of this problem from a different perspective. I want to introduce you to Radix sort. Some people might be familiar with this. Radix sort is a sort algorithm that's sort of like quicksort, but instead of picking a pivot, you just look at bits. So if you have integers that are evenly distributed, it's a really good way of quickly sorting them. So that's what I just said. Let's take a look briefly on how that would work. Here we have a bunch of integers, somewhat well distributed. You start with creating two cursors, one at the beginning, one at the end, similar to quicksort. You look at the first bits, and if they're different, you want zeros on the left, ones on the right. So you swap these two, and then you move the cursors. Look again, zeros, one. These are correct. Step. That one is wrong. So leave that cursor, move that cursor. Correct. Keep going, and swap those. Now all the ones are on the left, on the right, and all the zeros are on the left. That's the first recursion step. Then we can, recurse the left tree and recurse the right tree. So so the next step, now depth is 1, so we look at the second bit, do this exact same thing, swap those, move, swap those. So now this is sorted down to for the two first bits, right? And then we keep going. Right, we can keep recursing. So one interesting observation here is that the recursion in the Radix sort exactly matches the tree structure of the Merkle tree. Yeah, basically, right? You move items with zeros to the left, items with ones to the right, and then you keep sorting them like that. And if you end up with a range where all of the elements are either 1 or 0, then you know that you need to insert an empty node, like in the example. And when you get down to a range of 1 element, then you have a terminal node. So that's sort of the mapping. But right, so similar to the Merkle tree, we have everything that starts with 0 on this side, everything that starts with 1 on the right. So now we have, this is sort of like solving half of the problem. So we can start to think, like imagine a Radix sort that as it returns back up the recursion, it returns hashes. So let's try this example again. I'm not going to go through the entire algorithm, but so the first thing we do is we run one step of sorting and finding the sort of cutoff point where they divide. We recurse down the left side, do the same thing, sort them by the second bit, split them. All of these, the third bit here, all of them are ones, so we need an empty node. Compute its hash, because sort of we reach the end of the recursion. But then we recurse down the other side, sort, split, recurse, hash, recurse down the other side, sort, split, and I think you get it by this. Like now, this is the first time when we actually return back from 2 terminal nodes. So this is part of the call stack unwinding. We have 2 functions returning, two calls returning hash. We hash them together and return up, keep hashing, and then recurse down to the right. And more of the same, basically. Keep returning hashes up. So this is about 170 lines of Rust code, and it's all basically contained in a single function. And it has one of its main features or advantages is that the entire tree is laid out in a single array. So it's very compact and quick to access, relatively speaking. So you run one pass, one tree traversal pass on it, and you have the hash at the end. So this is about, that gives a speed up of 44. What does it mean? The slow version takes 44 times longer to run, which is, in our case, was actually somewhat important. This was showing up in our profiles before I rewrote this. So I think one of the takeaways is that the textbook version of this problem is perhaps the one that comes to mind first, and perhaps the easiest to implement. It might be the most verbose, and it might be verbose and it might be slow, but it might also be good enough. And it might be a good enough first version. But quite often, if you go further and work a little bit harder to find a different angle to a problem, you can get it even simpler and possibly even faster as well. But it takes work. So my punchline was originally thought. I originally thought it to be talking about you ain't gonna need it, the concept, but it doesn't really fit that, because it kind of makes sense to do the easy way first, even if it's the slower and more verbose version. So that's all I had. If you want to look at the source code, I have links up there for the two versions. And yes, Jonas.
The first one that you made.
Yes.
How would it handle partial nodes that you have part information on tree?
So that partial.
Like you were talking in the beginning that Merkle trees can prove that you have the correct root even if you don't have the entire tree.
Excellent question. The reason the Python version still exists is because the validation of proofs is still done in Python. The computing of the root hash is the only thing that I'm doing in Rust. That's something that happens more often. And so it's like the thing that showed up in our profile. Yes?
What's the consequence of a poor hash function? How does that impact? Is there risk of just poor performance because of deeper trees, or is there a serious problem? Are there serious
Right. So I would think so. If you have a poor hash function, first of all, you wouldn't be, if it's not cryptographic, you won't be able to do any of the proving. Right? Then you can probably trick someone.
Yeah.
But tree-wise, you get a lopsided tree, which in the Python version would be problematic because you would have to allocate a lot of empty nodes just to sort of build it down. I don't think it would be that problematic. It would give you more recursive steps and more hash function invocations, but it wouldn't allocate more memory, at least. All right. Thanks, everyone.